Hello friends. Welcome to my YouTube channel Chemical Adda. Please watch this video till the end to learn about the process of heat transfer through a wall formed out of a series of layers of different materials or compose a plane wall. And what is the formula for determining the rate of heat conduction through it? So, let's start by learning about the process of heat conduction through a composite plane wall. So a composite wall is one that is made up of multiple layers of various materials. Or we can say that, when a wall is formed out of a series of layers of different materials, it is called a composite wall. Like the walls of furnaces, boilers, and other heat exchange devices, because the walls of these devices consist of multiple layers. The layers of the wall of these devices may consist of a mechanical strength layer, such as fire brick, which provides high temperature resistance. Then the second layer may be made of low thermal conductivity material, such as insulating brick, which limits the transfer of heat. And lastly, the third layer that fulfills structural requirements and ensures a pleasing look, such as regular brick. So heat transfer through composite plane wall is calculated using Fourier law. Hence, according to this law, the heat transfer rate through a composite wall depends on the thermal conductivity, thickness, and surface area of each layer, as well as the temperature difference across the wall. Employing this concept as a basis, we will now construct the equation, which can be used to calculate the amount of heat transferred through a composite plane wall. Consider a flat wall that is made up of many layers and are made up of three distinct materials. Next, assume that the thermal conductivities of the materials that are used to construct layers are denoted by the letters K1, K2, and K3. Let the thicknesses of the layers be denoted as X1, X2, and X3 correspondingly. Furthermore, the resistance of each layer is denoted by the letters R1, R2, and R3. Next, let T1 represents the temperature of the face that is hot, and T2 represents the temperature of the face that is cold. And let T dash and T double dash represent temperatures at the internal faces of the wall. As we know, temperature decreases along the path of heat transfer. Hence, let me assume the temperature drop across the entire composite wall and denote it by the symbol delta T. Since the composite wall consists of three layers, there will be a decrease in temperature across each layer. Therefore, consider the temperature drop across the first layer as delta T1, the temperature drop across the second layer as delta T2, and the temperature drop across the third layer as delta T3. Also, let's assume that the layers are in excellent thermal contact. Let A represent the area of the composite wall, which is perpendicular to the direction of heat flow. So, in order to determine the rate of heat flow through composite wall, now let's apply Fourier's law to each individual layer of the wall. So according to Fourier's law, rate of heat flow through the layer 1, that is, through the material of thermal conductivity K1, is given by Q1 is equal to K1A divided by X1 into T1 minus T dash. From this equation, we can write T1 minus T dash is equal to Q1 divided by K1A by X1. Equation number 1. As we know, temperature drops across the first layer as delta T1 is equal to T1 minus T dash. Equation number 2. After comparing equation 1 and equation 2, equation 1 becomes delta T1 equal to Q1 divided by K1A by X1. Equation number 3. In a similar manner, let us compute the rate of heat flow through the second layer, which is made up of the material with the thermal conductivity K2. Hence, according to Fourier's law, rate of heat transfer through the layer 2 is Q2 is equal to K2A divided by X2 into T dash minus T double dash. From this equation, we can write T dash minus T double dash as equation number 4. Now temperature drops across the second layer as delta T2 is equal to T dash minus T double dash. Equation number 5. After comparing equation 4 and equation 5, equation 4 becomes. So delta T2 is equal to. Equation number 6. Similarly for third layer, which is made up of material having thermal conductivity K3, rate of heat transfer is given by Q3 is equal to K3A by X3 into T double dash minus T2. Equation number 7. Then temperature drop across the third layer. Delta T3 is equal to T double dash minus T2. Equation number 8. After comparing equation 7 and 8, we get delta T3 as. Equation number 9. Hence we get temperature drop across first, second and third layer as. While the temperature drop across the wall is equal to the temperature drop across the first layer plus the temperature drop across the second layer plus the temperature drop across the third layer. Hence we get delta T is equal to delta T1 plus delta T2 plus delta T3. Equation number 10. Now let's put the value of delta T1, delta T2 and delta T3 from equations 3, 6 and 9 in the equation 10. So we get. Now under steady state conditions of heat flow, all the heat passing through wall must pass through the layer 1 and pass through the layer 2 and layer 3. Therefore Q1, Q2 and Q3 must be equal and can be denoted by Q. Hence we get Q is equal to Q1 is equal to Q2 equal to Q3. Hence in above equation, we can write Q in the place of Q1, Q2, Q3. Hence we get. As Q is repeating in all terms, let's take Q as common, so equation becomes. Now after rearranging the terms, we get Q is equal to. Hence we get rate of heat transfer through composite wall. Q is equal to delta T divided by X1 by K1A plus X2 by K2A plus X3 by K3A. But as we know R1, R2 and R3 be the thermal resistances offered by the layer 1, 2 and 3 respectively. And their values are. R1 is equal to X1 by K1A. R2 is equal to X2 by K2A. R3 is equal to X3 by K3A. So after putting the values of R1, R2 and R3 in above equation we get. Q is equal to delta T divided by R1 plus R2 plus R3. This is the another form of equation for rate of heat transfer through a composite wall. Now if R is the overall resistance, hence we can write R is equal to R1 plus R2 plus R3. Hence final equation for rate of heat transfer through composite plane wall as Q is equal to delta T divided by R. So we get 3 equations to determine heat transfer through a composite wall. So that's all about heat transfer through composite plane wall. So keep watching. In the next video, we will discuss another topic. So, if you like my video, please like, share, and subscribe to my YouTube channel which is Chemical Adda.